Hi everyone. I'm really happy that you could make it, because otherwise it would have been such a performance for an empty room. Also, welcome to everybody who is following online. I hope you can hear me all right. I'll try to speak up and speak slow. If I don't get carried away too much, then that should work. Not to get you. So I have a few questions just to get you started off a little bit. Just quick shout outs. So if you see a question that you think you can answer, please do. So first one, what is the observable quantity in the semi-classical theory, and what is the observable in quantum electrodynamics?
Power for the semi-classical theory. Yeah. And in the last slide, you said probabilities for quantum electrodynamics.
Yeah.
Right.
Yeah, that's not quite observable, of course. That is the endpoint of what we do. Yeah, and really in the classical theory, it's all about powers, power densities or power per unit area. Okay, speaking of intensity, what is the physical unit of intensity?
What area?
Yeah. Well, exactly 1 per square meter per square centimeter. Yeah. Okay then. We have a check. Oh yeah. I'll try.
Maybe you can move the bucket.
Yeah. I'm not sure if I can move this one. Sorry. Can you hear me better now? Yeah. Accidentally plugged the whole thing. Okay. So let's start. What is the relation between the absorption efficiency and the absorption cross section? Or maybe start with what exactly is the absorption efficiency? The efficiency. I'm sorry. What is the? I first will throw what the absorption efficiency is. So you gave. I guess you answered the second question. What is the relation between the efficiency and cross section? So what is the efficiency? Yeah.
How is it? It's the efficiency. I'll go. The efficiency was that the effective absorption per area.
No, not quite. So the efficiency is really just the dimensionless number, so a percentage, let's say. So it is then the ratio of the amount of power that is absorbed over the amount of power that is. So it's purely dimensionless quantity. And then the absorption cross section, so that it really has units of square meters, so to say. That basically gives you the same information, only in different units. So you find that by multiplying the efficiency with the actual geometrical cross section. So people sometimes interpret it as like this is the area that the light sees from the particle. If the absorption cross section is really small, then a lot of light seems to just pass on the spectrum. And what was then the absorption coefficient? U of A.
the fraction of the light passing through divided or the light getting absorbed divided through the light constant.
No, that was the efficiency. So the absorption efficiency and the absorption cross-section are properties of one particle or one molecule, one absorber. The coefficient is a property of a bunch of them. So if you have multiple particles together, then the absorption coefficient tells you how the absorption of that collection is. There's a formal definition. The formal definition is it's the density of total cross section. So that means that you take the individual cross sections of all the particles, you add them up, and then you calculate, you divide that by the volume that particles with. So it gives you then a dimension of the area divided by volume. So per meter per unit length. Okay, then I'd like to know if we have a purely absorbing medium, so a medium in a cuvette set, say, a solution, and it has an absorption coefficient μA, then what fraction of the light would be left after a light beam travels a certain length L through that cuvette, through that medium? So how does that look like if you would make a sketch? So intensity as a function of yeah, so it's given by Beer's law, so that would be an exponential decay. The next slide, so I'm not going to draw it now. But then a related question is: so if now then, with that exponential decay, what fraction of the light is left after the light has traveled a distance, called L prime, that is equal to 1 over μA. μA is the absorption coefficient that had units per meter. So if you divide it, then you get length.
1 over E.
1 over E. Yeah. So that's about 32%. Yeah. Yeah. So I'll save the last question for just a moment. So yeah. So this is what it then would look like. So purely so simple exponential decay, and that's it's 37% actually now. If the length is exactly the 1 over μA, then only 37% is left. Okay, that brings me then to the big second topic that we discussed, absorption flattening. Can somebody give me a definition or a description of that effect mechanism? What was it about?
The stone of the nail presumes that the deeper you go into the sample, the more flat the absorption becomes.
No, it does not have to do with this graph anymore. No, it's so I'll give you a little hint. It had to do with the difference between so let's say you have the same amount of molecules and you have them suspended in a solution, or the same amount of molecules are contained in particles. And if you do both, if you do an experiment on these both situations, so you have the same amount of absorbed molecules, but you get a different experimental results in the absorption coefficient when they are in the solution or when they are contained in particles. And the absorption coefficient that you will measure in the particles is lower, and that's why it's called flattening. Yeah.
Yeah.
So did you? I asked you to go to website, download the spectra up there, and then see if you could calculate the absorption coefficient of a blood sample. Have you tried? Well, okay, well I did. So I would encourage you to try it out. try that. But let me at least talk you through it, because then you know what I'm talking about. So this was the website, and then if you scroll down, it ends with a remark like this: I want a typical spectrum for blood in units that I can understand. So these units would then be absorption coefficients, and these units would then be per meter, something like that. And this is then the explanation that is given on that site, but they forget the crucial thing. We want a spectrum for blood, so really the sample with the red blood cells in it. But the spectra that are given on this site are for hemoglobin, so for the absorbing molecules that are inside the red blood cells. And then there's a second thing in this, second peculiar thing in this derivation, that is this factor over here, 2.3, and that requires a little bit more explanation. The tricky part is that the tabulated data on that site is the so-called molar extinction coefficient, epsilon. So that is on the then also on the vertical axis in that graph. But it is kind of it's kind of a Lambert-Beers law, but then with a 10 based on power of 10, not on an exponential. So what we would have to do is, so this would be what you would measure in an experiment based on this data. But we, of course, seek an absorption coefficient based on Beers law. So what we would calculate would be µA, and then equal to natural logarithm of I over I0 divided by the cuvette divided by the cuvette length. And if you then fill in this 10-based expression, then we get a constant factor of ln 10 in there, and that ln of 10 is exactly that factor 2.3. But that's not really magic. That's just a person in this particular calculation. Okay, then the second thing is what do we know about blood? So we get the molar extinction coefficient, and we want to convert that into an absorption coefficient. So we have to know some of the properties of blood. So typical properties are 150 grams of hemoglobin in a liter of blood. So that is really in the blood sample as you would draw it, so not in solution. And the molecular weight of hemoglobin is given is 46 2,500 grams per mole, which results in a molarity of I'm not going to read the numbers of that, but of that amount of moles per liter. So we could fill that in, and that is actually what is done on the website, and then end up with a spectrum that looks like this. So this is then the absorption coefficient, and as you can see, it is just exactly the same graph, only with different units, but it's just a scaled version of the graph. So the problem is, so what happened here is that they took the values for hemoglobin, just scaled it up, and said, okay, these are the values for blood. They did not take into account here that these hemoglobin molecules are contained in the red blood cells, and that gives different values. So let's see what happens if we do try to incorporate that. So we have this situation. These are the numbers that we had on the previous slides, and also what you need to know here is what the volume fraction of red blood cells in blood is. That is called hematocrit. And the standard value for that in the healthy people is about 45%, 0.45. So that's one thing. The other thing is that we need to know the absorption coefficient of the hemoglobin solution inside the red blood cell. What we calculated on the previous slide was the absorption coefficient as if all the hemoglobin molecules would be in a solution of the same volume. So we have to scale that with the hematocrit. And then finally, we need to know the size of a red blood cell, because that was also part of the there's the formula. So what we need to calculate now is the absorption coefficient of blood. This formula, which has the hematocrit in there, and has the absorption coefficient of the substance inside the red blood cell. The top equation allows us to calculate that absorption coefficient, and we need to know something clever about the size of the red blood cells. That's also a little bit tricky because they are not squares and spheres, but donut shapes, with a volume of about 90 cubic micron. So now we can do a couple of things. What is R? That's the question. So we can treat them as spheres with an equal volume that will give you a radius of about 2.8 micrometer. We could treat them as cubes, which would give a radius of a size of the cube of about 5 micron. And of course, depending on what you pick, you will get some different answers. So that's a little bit the tricky part. There's this funny relation that says that. So what we actually did is we treated the red blood cell or any particle as a kind of mini cuvette. So we calculated how much light we put in the particle, how much light we get out of the particle. So we kind of treated it like a mini cuvette. And now it turns out that's a really funny result from theory, that the average length, the average intersection length of any shape. So you can take any shape and draw straight lines through it from one point on the surface to another point on the surface. You can prove that the average length of these lines is determined only by the volume of that shape and the surface area. And this vector 4. So this goes for shapes, this goes for cubes, but it also holds for these red blood cells. Yeah.
Are there any limitations on the volume or how they look?
I think it has to be a closed surface. I think.
Okay.
But otherwise, it's in this. There's a link to the paper there. You can look up. It's really fun. So then I dove a little bit further in the literature. I found this one with some experimental results. They claimed that the volume of the red blood cells that they measured was actually slightly a little bit larger than the 90 cubic micron that I thought it was, but they found 99. And they somehow established a surface area of about 150 square microns. So, so using these numbers, that would lead to an R of about 2.7 micron. Well, you can see all these numbers are pretty more or less in the same ballpark. So I used this 2.66. Doesn't really matter for the effect, of course. Okay, what you now get is this calculation. So the solid lines here are using this flattening effect from the previous slide, and the dotted lines are the results we started out with that were also on the website. So for the hemoglobin solution, and as you can see, especially at the locations where the absorption coefficient is really high. So let's say here at about 450 nanometers, there the absorption coefficient of the blood is really much lower than the absorption coefficient of the hemoglobin solution. Now remember, these solutions, both these samples have the same amount of absorbed molecules. It is just that because they are now contained in the particles, is that the absorption coefficient is lower. On the other hand, you see that if you go to wavelengths here where the absorption coefficient is not that high, then the effect is also almost not there. It's really minimal. So it's really what happens is that it really just flattens the absorption peaks at higher values, and at lower values nothing so much happens. So there's a little plot on the right here that shows you that actually this ratio of the suspension over the solution. Absorption coefficient of the suspension over the absorption coefficient of the solution, I should say. If the absorption coefficient of the substance inside the cell is really low, then that ratio is 1, so the absorption is almost equal. And if you go to higher absorption coefficients within the particles, then the ratio gets much smaller. Yeah.
Where do the peaks come from?
In a spectrum like this, that is really just the molecular composition of not composition, the shape of the molecule.
Okay, it's just the shape of that.
Yeah, it's just the shape. So what you see is, so hemoglobin is this kind of this ring structure with all of these side strings to it, which would give you, if you have the pure hemoglobin, would then give you this absorption spectrum, so different absorption strengths and different wavelengths. And once it starts binding oxygen, there is really a deformation change in the molecule. So in 3D, I think the hemoglobin molecule stands a little bit like this, and then if it attaches to oxygen, or if oxygen attaches to it, it gets more or less a shape like this, and that leads to changes in these absorption peaks.
So in the end, it's a lot about the precipitation.
Yeah.
Can we derive the absorption coefficient generically, or just shapes of molecules, or do you are completely dependent on measurements?
Yeah, I think you can have some. It's kind of a linear combination. So if you have certain groups in the molecule, you can expect certain peaks to show up or not. I'm not sure if you can precisely derive it, but hemoglobin, as the name already suggests, has heme groups in there. If you have other molecules which have heme groups, then usually these absorption these bands show up in all of them. So in that sense, you can predict it a little bit what you question. Okay, any questions about this? Try it. Okay, so then I want to switch gears and now leave the absorption aside a little bit and go to scattering. Part of it will be familiar because also for the scattering process we can define efficiencies, cross sections, and coefficients, and as you will see, the scaling works more or less the same. So I'll introduce that by some phenomena that we can see on a sunny day, so not today, it's unfortunate. And then I'll go through this list. So let's go. This was the image that I started out with, so kind of an experiment what would happen if you put an absorbing substance in a cuvette and you shine light through it. You would see that if you increase the amount of absorption, then the distribution of light changes a little bit. It gets less, of course. If you do the same experiment, but now with a scattering solution, the effect is it's a little bit more. It is a little different. So on the left-hand side, it's just water, and then we add increasing amounts of small particles, small scattering particles to the water, and look at the distribution of light. So in the second experiment here, there's a lot of light that is not scattered yet. So you see it's still propagating along the incident direction. And as you add more and more particles, more and more light is scattered very soon. So the distribution of light becomes a little bit closer to the front surface. And here actually a lot of light. So the scattering is really what you really see in scattering is really a redistribution of the light. So it is not absorbed in this case, it just changes direction. So loosely defined as the change in direction of light. And we can define these same quantities. So let's start with scattering efficiency. In absorption, it was the ratio of absorbed power over incident power. For scattering, it is simply the ratio of scattered power over incident power. You can then multiply this scattering efficiency with the geometrical cross section, and you would get the scattering scattering cross-section. And of course, that also means that this operation tells you that the scattering cross-section is also the ratio of scattered power over incident intensity. Work out the units and you'll see that it figures. And lastly, the definition of the scattering coefficient is also analogous to that of the absorption coefficient. It is the density of total scattering cross-section. So you take the scattering cross-sections of all the individual scatterers, you add them and divide them by the volume. Some kind of a little thought experiment, because it's not such a clear day, but you probably have already encountered these things quite some time. So why is the sky blue?
Because of the different scattering patterns for different waves of light that are sent that are contained within white light. Because blue light gets scattered through most of all the colors. It is what we see reflected most into our eyes. Therefore, the sky appears blue because the light of the sun is scattered through all the dust particles, air molecules, and other gases that are inside the Earth's atmosphere.
Yeah, that's exactly true. I really have nothing to, almost nothing to add to that. So the geometry would be this: if you would look straight at the sun, which of course I do not recommend, you would see white light more, mostly white light. But if you look then to the sky away from the sun, then you will see light that has of course is not directed to your eye. It has been scattered by airborne molecules towards your eye. So that is that's true. Because these molecules are very small. It also goes for dust particles. They scatter blue light more efficiently. That's why the sky away from the sun appears blue. The sky just around the sun will appear more whitish. This is called this process is called Rayleigh scattering, after the guy who described it. And it is found that the scattering, it's a scattering coefficient here, it also goes for the scattering cross-section, is proportional to the inversely proportional to the fourth power of the wavelength. Blue light, of course, is a short wavelength. Red light, for example, would be longer wavelengths. So you can see that that blue light is exponentially more scattered by these small particles. So lambda to the power of -4. Okay, then why are clouds white? Can you think of an explanation that follows more or less the same reasoning as here?
I would tend to say that they're usually so random that everything just gets added again. White.
Yeah, I think. Yeah, so that's. I'm sorry, I skipped one. Apparently, we'll get back to the class in a moment. If you this also happens. If you look at the if in daytime you look at the horizon, that becomes whitish again. So you start if you look at the zenith of the sun, the sky looks white, and if you look off a little bit off to the sky, it's bluish, and then if you go further to the horizon, it starts being white again. Yeah, simply because all these eventually all the light will be scattered somewhere. And if it in the horizon is obviously far away, so in the end, all these, not only the blues but also these greens and reds will also reach right. Yeah.
Is that also why for example, the sky during dawn or dusk is usually red or purplish? Is that also because at the end of because it needs to go through so much atmosphere, only the red light gets scattered so little that only the red light remains?
Yeah. Yeah. That's true. So this is the clouds, and so what you said, it's diffusing a little bit. I think that that's more or less correct. If you look at if you try to look for an explanation more or less in line with what happens with the molecules, in clouds you have water droplets, so you have larger particles, and for these larger particles, the efficiency of scattering as a function of wavelength is less dramatic. So where it's scaled for the small particles, it's scaled with lambda, the wavelength. Firstly, with the wavelength to the 4th power is now, well, let's say, quadratic or something. So empirical numbers is at 1.7 is an empirical number. So also the longer wavelengths get scattered quite efficiently here. So that means that actually all the sunlight is then scattered towards your eye, and then it looks whitish. Here is then your evening sky or your morning sky. So one effect is that because the distance from the sun to your eyes at your horizon is now pretty long, that means that if you look directly at the sun, the blue light is still scattered out. So what remains are the red lights. So that's why it looks reddish. And what you also have is that around the sun. If you look at low, so there's at low altitudes above the Earth, there's all kind of dust and so a little bit larger particles there that also scatter the light, and then again blue is removed if they travel a long way to your eye. So all that adds up together to a reddish. Okay, so the bottom line of this is that these scattering properties are then determined by the interplay of the particle size and the wavelength of the light. So if you have particles that are small compared to the wavelength, then there is a strong dependency on the wavelength, so lambda to the power -4. If the particles are comparable in size to the wavelength, somewhat smaller than the wavelength, then in general it will be with a certain factor that is less, that's much less than 12. So now what does that mean for tissue? Well, we have a lot of differently sized structures inside the tissue. So if we illuminate that with a certain wavelength, we can expect different responses for the different structures. So if you look at, so this is a list of what you can encounter as a scatterer in tissue. So that goes from very small, from proteins in the size of nanometers, all the way up to cells that can be micrometers or even larger in size. There's a line here that says lambda visible. That is not where the visible wavelengths start. The visible wavelengths start around 300 nanometers. But this is this line indicates where actually the scattering can be picked up. So scattering from these macromolecular complexes, so in the order of 1 to 10 nanometer, they already give scattering signatures using white light that you can picture. So it's much. So the structures themselves are much smaller than the wavelength, but they do scatter light, and so you do get response. Now, of course, with that knowledge, we encounter kind of the same problem once again. So we can try to calculate how these different sizes would scatter light. So that would be the forward problem. In the end, of course, we're going to do measurements of scattered light, and we would like to know what actually caused it. So, but we first have to. We'll first look into this problem before we can actually start thinking about the other one. So then the question becomes: at what size should we describe the scattering process? Again, we can make a choice. The smallest possible scale to look at would be a dipole for very small molecules. Then, of course, we could look at the scattering of, let's say, a red blood cell, another particle here, for example, or we could jump immediately to the larger structures like the vasculature or a bulk piece of tissue. We'll start here now in the middle at the particle level. So let's say we can we have a particle, whatever size, with an area, geometrical area G, cross-section area, and also that we can measure somehow the amount of power that is scattered by the particle if we put in some incident power. And we calculate, just as we did for the absorption coefficient, we calculate the scattering efficiency, the power ratio, so the scattering power over the incident power. If you multiply that efficiency with the geometrical cross-section of the particle, we get the scattering coefficient, so units of scattering cross-section, units of area, and we can rearrange that. We can rearrange that a little bit so that the scattered power is equal to the intensity times the geometrical cross-section. So the scattered power here is given by the product of the scattering cross-section and the incident intensity. We're going to use that relation pretty extensively. So what we want to do is calculate or find an expression for the scattering cross-section. And what we can do is try to express that in terms of the things that we know, the things that we can measure. So let's say we can measure the scattered power, we can control how much light we put into the incident intensity, then we should be able to measure the scattering cross-section. So measure the power and then divide by. So how to do that? So we take this particle, we put it in a large imaginary sphere, which has of a certain radius. There's light incident on the particle. It scatters the light in all directions. So let's say we can measure the light that goes through the surface of this imaginary sphere. So that means we could calculate the scatter power as the integral of the scattered intensity over the area of that imaginary sphere. Just we have the scattered intensity that goes through this area. If you multiply it, you get pi. This integral just adds all contributions together. To do that calculation properly, we have to look at the intensity that actually goes perpendicular to the area of that sphere, and that's why this normal vector is here, and this inner product is also there. That's the reason for that. So then the question becomes, or then the task becomes, that we have to find an expression for the scattered intensity. And once we have that, we can integrate it over the area of that sphere, and from that we can calculate an expression for the scattering cross-section. So let's have a short break and then dive into that calculation. So we said 10 minutes. Is that okay, or do you want longer? 10? Okay, we're ready to continue. So we left off here. The task is now to get an expression for the scattered intensity, and then after that we will integrate that over the surface of such a sphere, and then from that calculate the scattering cross-section. All right. So to get the scattered intensity, we are going to start with first calculating the scattered electric field, and then square that or multiply it with its complex conjugate, if you like, to get the scattered intensity. So let's assume that this particle is illuminated with a plane electromagnetic field. So in the complex notation, it is this complex exponential with a wave vector k in, so that is the incident direction, the particle will scatter light in all directions, of course, but we are going to look in the direction of given by the factor scattering direction. So it is as if we would put a light source here, and if we would put a detector there. We're going to try to calculate what we would pick up there. So the magnitude, just to refresh, the magnitude of these wave factors is the wave number k. K is 2 pi over lambda, lambda the wavelength. So that relates to the color of the light. We are considering so-called elastic scattering, which means that the color of the light does not change. So these two factors k in and k scattered, they both have the same magnitude. They have different directions, but they have the same size, the same magnitude. So this is then the expression for the incident electric field, and we're going to look at the amplitude. So the amplitude of that is 1. That's an arbitrary choice. But, it just makes the equations a little bit simpler. And we're going to look for a scattered field that has this form. So what you see here is that it has it also has this complex term over there. It is a sphere. The scatter field will be a spherical wave. Spherical wave that means that the light is, well, as it spreads out, the conservation of energy then requires that the intensity drops out with 1 over r squared, which means that the field will drop off with 1 over r. So that is why so r is measured along this direction, the distance r. So that is why that shows up there. Also in the denominator is the wave number k. That is just to make the denominator dimensional, so it does not have any other. And that also goes for the complex number I in there. That is only for convenience. So there's no physical meaning. It's just for convenience. And then in the denominator, that's where the denominator is where the exciting stuff happens. Is the amplitude function s, which is a function of the incident direction and the scatter direction. So s in and in there in bold are unit vectors in the direction of incidence and the direction of observation. This is a function that describes how the optical power of the light is redistributed. So it tells you how much light essentially coming in from the incident direction is redistributed into the spectral direction. Yeah. Why would you do that? Okay. Didn't expect that. So a spherical wave in the far field, that means that the electric field scales with 1 over r, and a complex redistribution function or amplitude function that describes how the energy is redistributed. So given these two equations, we just a little bit of manipulation in the notation. We're going to write the wave vectors as a function of their magnitude and the unit vector. Yeah.
Spherical wave scales with 1 over r.
The spherical, now the intensity scales with 1 over r squared.
Okay.
But we're one step above that for the electric field. That scales with 1 over r. So that if you square it, it will scale with yeah. The terminology is the spherical wave. But,
okay, that makes sense.
Yeah. So that is for both the unit vectors in the incident and the scattering, incident and scattering direction. We place the particle at the origin of an of a coordinate system. We're just going to set the incident field at that position to E in, so without any R dependence anymore. So then starting with the top equation, we separate the exponentials for the R dependence and for the oscillation, the time oscillation and the T. Like this. So then the total, and then we do the same thing for the scattered field. So we have this term again for the redistribution, for the spherical wave, and the split exponentials. These are then the two equations we kind of. So let's first isolate from the incident field an expression for E omega t. So by bringing one of the exponential terms to the other side of the equation, and then substitute that expression for E omega t, the exponential E omega t, into the scattered field. We can do that because the scattered field and the incident field were in phase; they oscillate at the same frequency. So we can make this a substitution. Doing that now gives us no temporal dependence anymore in the scattered field. Just an expression in terms of the incident unit, incident light in the scattered direction. So we can reorganize that. We can combine these two exponentials in one term. So we now have that the scattered field is proportional to the incident field. It has this term that describes the spherical nature and the redistribution and the phase term. That's the same slide as this. So for the intensity, then, if we now have the expression for the scattered electric field, so the scattered intensity, we multiply it with its complex conjugate. So that means that the phase terms here basically will drop out. That's convenient. And the expression is like this. So the square of E in will just be the incident intensity over here. The denominator will evaluate the k squared r squared. Somehow I squared is -1, but that is scooped up in I don't know where. And then the amplitude function is also multiplied with its complex conjugate in the denominator. So the final result. So the amplitude function is complex as well, but if we write that also in this exponential form, there should be an E in here, I'm sorry. So a magnitude and a phase term, e to the power E sigma. Then by multiplying with the complex conjugate, also that term will drop out, and we end up only with this expression. So the scattered intensity is proportional to the incident intensity, of course. We have the spherical nature wave here, our r squared made dimensionless by the factor k over here. And then again, this term in the denominator that describes the redistribution of the light. So now we can go back to the original equation. So the scattered power was given by the scattering cross section times the incident power. Scattered power was also equal to the scattered intensity integrated over this hypothetical sphere surface. So by combining these two expressions, we can isolate the scattering cross section. So we have to find we found this expression for the scattered intensity. What we now have to do is integrate that over that spherical surface, and then we have our scattered power. So again, just a small sidestep for the coordinate system that we use, and so that will help us to perform this integral. So this was the particle placed in the origin, and unit vectors in the incident direction and the direction of observation, the scattered direction. It is more convenient to treat this problem of this integration in a spherical coordinate system. So that means that we have a polar scattering angle there. That is angle of the scattering factor with the z-axis, polar scattering angle theta, and then we have the so-called azimuthal scattering angle. That is the angle with the x-axis of the projection of the scattering factor in the xy plane. Okay, that means if we switch to this coordinate system, that we can write s squared, which was a function of these directions, we can write that ultimately as a function of these angles. Also, in the spherical coordinate system, we can find we can calculate the unit area on the surface of the sphere. That is given by r squared. R squared is then the radius of the sphere, sine theta d theta d phi. That would be the elemental area on the surface of the sphere. So with that, we can change this integral written here, so integration of the area of the sphere in spherical coordinates, which makes life a little bit easier. So we have combining all the equations, we have a scattered power is proportional to the incident power, and then this integral term has here the inner product of the direction of observation with a normal to the sphere surface. Well, that's easy because we're looking far away at the sphere, so these two directions are always aligned. So this part will just vanish. We have r squared here in the denominator, but also here by virtue of that dA element, so that will drop out. So what we end up with is an expression as theta s squared of theta and phi divided by k squared, which should be integrated over sine theta d theta d phi. So that written here that integration has to be carried out over the whole sphere. So that means that theta is integrated over 0 to pi, while phi is integrated over 0 to 2 pi. Is it clear why that is? So if you want to integrate, over a whole sphere, it's more like what's into y. So you have this. You first start integrating this part, and then you turn the whole thing around, and then you cover the whole surface of the sphere. So if you would integrate over 2 pi, in both cases you would have 2 times the sphere. So that is why the integration of theta only runs from 0 to pi, and from the other one from 0 to 2 pi. Yeah.
So you integrate. So the theta is both integrated from top. Yeah, I see.
No. Super. All right. So then finally, we can compare these two equations, and then the expression for the scattering cross section now drops out. So k is a constant that can be brought out of the. So this is the result is for the scattering cross section, and it is expressed in terms of this redistribution function. All the information about the scattering process is contained in this s squared function. So the total strength of scattering, because that will translate into the scattering cross section and also the angular redistribution. It is sometimes, most of the times, it's convenient to split these two quantities. So the total strength and the angular redistribution. So you can split this equation as follows. So first, rearrange it a little bit. So bring k squared to the left-hand side of the equation, and then define a new function, a normalized function, as theta. I'm sorry, p of theta and phi is equal to s squared theta, normalized. It's basically a normalized version of s squared theta. So you take the function and you divide it by the whole area of the functions. This function p is called the phase function, and because of this normalization and because of this rearrangement, contains only information about the redistribution. So not anymore about the strength of scattering, but only about the redistribution. It is normalized. That is what we did here. it's normalized on theta and phi. Or, theta and phi both form a solid angle, so we could also say it is normalized on solid angle. And because it is normalized, you can kind of regard it as a probability function for scattering into a certain
I'm a little bit lost. What is PV here?
P of theta. So it's we started out with the top equation, which was the scattering cross section, which had in the integral the function s squared. That s squared contains information about both how strong the scattering is and about the directions. What I want to do is split these two. So I want to have one expression later on for the scattering strength and one expression that describes the angular distribution.
Okay.
So in order to do that, from the top equation, we bring k squared to the other side of the equation. So the end of this contains, still contains information about the strength, but by normalizing it, that falls out. So now it only contains information about the angles, about the redistribution.
Okay.
That's so it is normalized. So that means that if you have this function p, whatever the format is going to take, if you calculate the integral over solid angle or over sine theta d theta d phi, the answer should be 1. That's because of the normalization. So what you can now do is it's a little bit trivially, we can write the scattering cross section here as the product of the scattering cross section and the integral of this phase function. And because we can do that because of that normalization, we should trivially evaluate to 1. There's a reason for doing this, because now I can define a so-called the name is differential scattering cross section. It's a little bit, the name is a little bit unfortunate because it has nothing to do with differentiation at all. But basically from what you see here is it's differential scattering cross section containing both information about strength and direction, separated into two. One quantity that tells us how strong the scattering is, the scattering cross section, and one quantity, the phase function, that tells us about the angular redistribution. So it's not really very exciting here. It is just a little bit of manipulation of the terms in order to separate these two effects. One note here is that very often we'll find that this phase function, generically written here as p of theta and phi, actually contains no dependence on phi at all. It just depends on the polar scattering angle, and over the other angle it's symmetrical. So if that is the case, then you can carry out the integral over 0 to 2 pi d phi. You can carry it out separately, and that will just give you a constant 2 pi. So that simplifies matters a little bit. Now, this function by itself, it's not so convenient to work with. If you want to calculate certain properties, then the whole function is a little bit hard to treat. So what we usually do is try to parameterize that phase function into a single parameter. That gives us information about how it behaves. That parameter is called the scattering anisotropy. It has a symbol G, and its definition is given. Its mathematical definition is given there. It is cosine theta, and then multiplied with the phase function, and then integrated over its order. Which means that if you regard the phase function as a probability density function, if you then multiply. So what you do here now is you take cosine theta and you multiply it with the probability of a given theta or a given theta phi, and then take another cosine theta, multiply that with the probability itself, and then add a mod. That's what the integration is. So you're calculating an expected value, an average value of cosine theta. So that is then the other that is then the other definition. It is the average of the cosine of the scattering angle. Because it's cosine, it has a value between -1 and 1. There's a couple of things to keep in mind here. It is cosine theta, so you have scattering in a given direction. Theta is the angle between the incident direction and the outgoing direction. So what cosine theta actually does is project the scattering, project the amount of scattered light onto the incident direction. So it tells you the fraction of light, the fraction of scattered light that still propagates in the incident direction. A measure of the amount of forward directed light. You can have an average scattering angle and an average cosine of the scattering angle. Be aware of that that the cosine of the average scattering angle is not the same as the average of the cosine of the scattering angle. That is an important distinction. So keep that in mind. So what can we have with this one? So if G is 1, the average cosine of the scattering angle is 1. That means that all the light is scattered in the forward direction. It's just as like no scattering took place at all. The light just retains the incident direction. Likewise, G is -1 implies that all the light is scattered exactly back in the direction where it came from. So like a pure reflector. And if G is 0, that is a little bit more complicated case. If the average of the cosine of the scattering angle is 0, then we can have a couple of situations. We can have there's an equal amount of light scattered in the forward directions as into the backward directions, because then the average cosine averages out to 0. It does not mean that light is scattered equally into all directions. So if light would be scattered equally into all directions, then the average cosine would be 0. But if the average cosine is 0, it does not imply that all the light is scattered equally into directions. And I'll give you an example, an extreme example. So let's say you have a particle that scatters light exactly in the forward direction and exactly in the backward direction in equal amounts. In that case, the average cosine would be 0, but still you would have only 2 directions. There would be no light scattered into any other direction.
So it would be not so much a sphere as a sort of ellipsoid.
Could be, yeah.
Just that when you cut it in half, both sides would be symmetrical.
Yeah. So I'll give you a few examples of a phase function. For the moment, never mind how this was calculated. So what you see here is a scattering angle here on the horizontal axis. The magnitude of the phase function on a log scale on the vertical axis. And the inset shows a polar plot of how the light is redistributed. So in this case, the light is coming in here across the 180 degree, along the 180 degree line. The particle is then in the center of this polar plot, and the red curve shows you how the light is redistributed. So this is a pretty large particle. It is twice, the radius is twice the wavelength. And from this polar plot and also from the graph here, you can see that most of the light scattered predominantly in the forward direction, so in the direction where the light came from. So it is a little bit redistributed, as you can see, but most of the light scatters in the forward direction. If you would calculate the average cosine for this situation, you would end up with 0.999 and then something, so very close to 1. Most of the light, almost all of the light, goes in the forward direction. If you now take a particle that has a radius of exactly the wavelength, so a little bit smaller compared to the wavelength, then you notice some changes. So still a lot of light is scattered in the forward direction, but not as peaked forward anymore. It is distributed over more angles, which you can easily visualize here, but you can also see that in the graph itself. And if you then calculate the average cosine of the scattering angle here, the anisotropy, it will be 0.93, so less than what we had in the previous graph. And now an even smaller particle, so radius half the wavelength. Still, almost no light scattered back. In the polar plot, you cannot even see it. On this graph, you can see that there is some light scattered in the backward direction, but still most of it is going forward. Be it in a little bit broader cone now again. The anisotropy, the average cosine of the scattering angle in this case would be 0.75, so it gets lower. And then finally, a very small particle. So size is a tenth of the wavelength. Now we clearly see that light is scattered both in the forward hemisphere and into the backward hemisphere. So in the polar plot, you can see it in the graph as well. Calculating the anisotropy now gives a value of 0.1, 0.12. So that's already pretty close to zero. So now we have a situation where almost equal amounts of lights is scattered into the forward and into the backward hemispheres. So in summary, that the effect is like this. If you have a particle that is large compared to the wavelength, then most of the light is scattered along the incident direction. This is called anisotropic scattering. It gives you an anisotropy, which is how G is called, value of that is larger than zero. And if the particle is small compared to the wavelength, you have isotropic scattering, and this factor G will be close to zero. And again, note that G0 does not mean that the phase function is uniform. That does not mean that the light is scattered equally into all directions. That is just a special case. If it would be scattered purely in the forward and purely in the backward direction in equal amounts, G would also be. Okay. So what have we done so far? So we calculated an expression for the scattering cross-section, but the actual theoretical can is kicked down the road a little bit because we still don't have an expression for s squared of theta and phi, and that is what's contained in the information. What we do have is the scattering efficiency, the scattering cross-section, and coefficients, simply because we applied the same definitions that we had for absorption to the scattering process. And then this directionality was captured into a couple of functions of theta and phi. So we had for the electric field, we had the amplitude function, capital S of theta and phi. If we squared that, multiplied it with its complex conjugate, we had the s squared function, small s squared. If we normalize that, we got the phase function, and then we multiplied the phase function with the scattering cross-section again. We got a differential scattering cross-section, so that is admittedly a little bit overcomplicated. But, each of these has its own uses. And then finally, to summarize the phase function into a number that tells you its behavior, we have the scattering anisotropy. All right. I'm going to switch, I'll not switch topics a little bit, but dive a little bit further now into this s squared function. So I'll briefly gloss over this because this is just what we discussed in the last few slides. So let's look at these different regimes again of particle sizes. So we have this whole distribution of possible scattering particles inside the tissue. Let's say we illuminate with visible light, so we can make kind of distinction into particles that are much smaller than the wavelength. So let's say up until 30 nanometers or so, that would be typically cell membranes. Particles that are almost the size of the wavelength, so that would be cellular components, the nucleus, for example, and then the larger particles that could be cells. So these smaller particles, we actually encountered them already a little bit when we looked at the blue sky. So these particles that are smaller than the wavelength that predominantly scatter the lower wavelengths. This was called Rayleigh scattering, scattering by particles much smaller than the wavelength. And the simplest way to describe that scattering is really in the classical picture. The classical picture used bulk material properties to describe what was going on, and the property that we need here is the electric polarizability of the particles. And electric polarizability essentially is just the ability of a material to form dipoles. So you have this electric field that is incident on a piece of material. Due to that, the charges in the material start to oscillate due to that field, and the amount of separation that you can get between charges is the ease with which you can form dipoles due to that oscillation is quantified by this polarizability. Now, this oscillating dipole that's caused will in turn emit an electromagnetic wave, and that is then the scattering. We're talking about small particles here, so that can be individual atoms or small molecules, but also very small particles. So they all follow this Rayleigh scattering pattern. So Rayleigh, as you can see, is of a somewhat older generation. That older generation did not work as much with mathematics as we are used to. They did things more in terms of reasoning and describing. So, which I think is really admirable. So he just reasoned how this scattering should behave, and then later found the equations and the mathematics around it. So just by observation, he found that the scattered field amplitude. So he could observe intensity, of course, but he knew about the relation of electric field and intensity. He found that the scattered field amplitude must be proportional to the volume of the scattering, just by experiment. He also noticed that it emits a spherical wave, so that means that the intensity would scale with 1 over r squared, and that implies that the electric field is inversely proportional to the distance. So that's close with r. The scattered fields and the incident fields were in phase, so the scattered field itself must be time independent. There is no lag in time scattered field as compared to the incident field. And it must be related. The input field must be the scattered field must be related to the incident field by some dimensionless function, because it has the same units. So that means that we could write the scattered field as equals to this function f times the incident field, and consequently the scattered intensity is equal to f squared times the incident intensity. Now, by combining all these requirements, we had that f was, so the proportionality function f is proportional to the volume, the first bullet point. It is inversely proportional to the distance, the second bullet point. It must be dimensionless. So that means that volume here, we have distance here, so we need area. So we put the wavelength here to make the whole function dimensionless. And then if we square it for the intensity, that means that the scattered intensity is now going to be proportional to the volume squared, which means to the radius to the 6th power, and to the squaring this one to the wavelength squared, to the 4th power, and also to the distance squared, of course. Okay, now without derivation, I'll just jump a little bit ahead and give the whole expression for the scattered intensity. On the top there, it is a function of the distance from the particle. and it's a function of scattering angle theta. And this is one example where there is no dependence on that azimuthal angle, so there is no phi in the expression. Just the proportionality with the 4th power of the wavelength is expressed there with k to the 4th, k is 2 pi over lambda. Alpha, the factor of alpha is the polarizability of the particle, which is given by, is determined by the refractive index of the particle, like stated there. And then the volume is in there for the polarizability, the radius to the 3rd one. Okay, so if you now take that expression for the intensity and calculate it with and compare it with the general expression for the scattered intensity that we had previously. So it is proportional to the incident intensity. We have that on both equations in there, well, I0 there. In the second equation, it is we have the product of the scattering cross section, which describes the strength of the scattering, and we have the phase function green, which describes the angular part. These terms are also indicated in the same color in the top equation, and then there's the R² term for the spherical level. So we can combine these or split these terms, and we see that the phase function here, P of theta phi, is going to be proportional to the terms that describe angle in the top equation. So just a side, why proportional? Why not equal? Yes, exactly. It has to be normalized, and this as it is not normalized yet. So, that's exactly right. And then also, if you group the terms that are not dependent on angle, then we find again the expression for scattering cross section over here. Yeah, this basically explains the normalization. So it has to be normalized on the whole domain. So if you integrate this function with the proportionality constant from 0 to 2 pi d phi, 0 to pi sine theta d theta, it has to be 1. So then if you do that, then the proportionality constant will drop out. Okay. I've put it in an exercise, but I'm not going to let you do it now because I think on Friday it's more convenient to just continue and then have you go home early instead of keeping you here until 5 o'clock. So this is then for later a little bit. The question is to show that this proportionality constant, in fact, is 3 divided by 16 times pi. Okay, this is the result so far. So for the small particles, we have Rayleigh scattering. So if we make a diagram of scattering cross section on the vertical axis and particle radius on the horizontal axis for a given wavelength, 500 nanometers, and a given set of refractive indices, we can calculate the scattering cross section as it is determined by Rayleigh. Right. Now let's look at the other end of the spectrum, so over here, and look at particles that are much bigger than wavelength. So really big. Think of observable with your eyes. So the intuition is that such a large particle would simply block all the light that is incident.
Yeah, you see it, it's more or less microscopic anyway. So
yeah, so it's maybe it reflects the light or it absorbs. What's absorbed is gone, but what is reflected is also gone. So you would say, okay, the absorption cross section for blocking for scattering is equal to the geometric size. It turns out to be a little bit more complicated. we have to look into all the effects that take place here, and then we'll see that it's a little bit complicated. So first, the first effect that can happen is simply reflection. Light is reflected back from this large particle, and that counts as scattered light. So that contribution is there. There's also a contribution from refraction. So light can enter this particle. So let's say it's a glass particle. Following Snell's laws, it will break into the particle. It will reflect back from a back surface and then enter or exit at some other direction as well. That Snell's law has the refractive index in that. The refractive index is dependent of wavelengths, so this process will work differently for different wavelengths, and of course you can recognize that this is how rainbows form. So the white light is incident on the water droplet. The different colors get refracted by different in a slightly different ways. But this also counts as scattered light. It's a change of direction. So it counts. So if we now take these two effects, refraction, reflection, assume that the particle does not remove light by absorption, then the combined efficiency, so the amount of power that is redirected through reflection and through refraction is equal to the incident power, which is conservation of energy. So that would lead to an efficiency factor of 1, and that would lead, if the efficiency is 1, that would lead to a cross section. So cross section for reflection plus refraction that is equal to the geometrical cross section of the particle itself. So that is just as expected. But there is one other phenomenon to occur. So this concerns only the light that hits the particle. There is also light that does not hit the particle, but that slightly passes the particle. And that effect is called diffraction. I think you have encountered that, of course, at least probably in high school, where it was explained with water. It is the effect that happens if a wave tries to move, in this case, past a small hole. So we have a wavefront here, plain wavefront here that hits the screen. The screen has a small hole in there, and you can see the spreading out of the waves as it moves along. In optics, it is explained by Huygens' principle, which states that every point in this hole forms a new quasi new source which emits a spherical wave, and the addition of all these spherical waves makes that this wavefront diverges. And we see that in optics as well. So if you put a laser beam through a screen with a small hole in it, and you look you put a detector far away or a camera far away, you can see this these kind of patterns, these kind of wave patterns. So diffraction is so that's also a contribution to that you need to take into. The scattered field will then be a superposition of the light that is reflected, the light that is refracted, and the light that is diffracted. And all these fields, these three contributions, can interfere. They can strengthen each other. They can dampen each other. So depending on the geometry, it depends a little bit on what you will get. So we now have to take a slightly closer look to this diffraction product. Diffraction effect, and we do that by using or looking at Babinet's principle. This is Babinet, also from a slightly older generation. I see that I made a typo. The guy did not make it into 200 years old. But Babinet's principle says that the diffraction pattern that is formed by a body, some kind of shape, is equal to that of its complement. So if you take a screen and you cut out a hole in there which has the same shape as the body, so the projection of the body, then these both will produce the same diffraction pattern. So that means that in the classical experiment of the previous slide, if we had a hole in the screen and we would illuminate that hole, we would see a diffraction pattern in the end. Now, Babinet's principle tells us that if we replace that hole with a particle, the particle will cause the same diffraction pattern. So diffraction also causes redistribution of the incident light. Now, the amount of light that is incident on the particle, or the amount of light that is incident on the hole, is exactly given by the geometrical cross-section. So that means that there is also an efficiency for diffraction that's equal to 1. So we now have the situation where we had an efficiency for reflection and refraction that was equal to 1, and we have an efficiency for diffraction that is equal to 1. So adding these two together, we end up with the total efficiency for scattering just being just a redirection of light, that is equal to 2 for these large particles. So these large particles have a scattering cross-section that is twice the geometrical cross-section. They cause the change of direction of light. Basically, the power of the light that has changed direction is twice the amount of power that is incident. Now, this is quite counterintuitive to wrap your head around, and for that reason, it is known as the Extinction Paradox, because it seems a little bit paradoxical that a particle would remove twice the amount of light that is incident. It's also an effect that you will not observe in daily life. You can observe it in an experiment where there is no visible shadow, and then you should really think of. Let's say you have a comet passing somewhere in outer space, which is illuminated by a star even farther away. So you will not see, with any detector or any telescope, you will not see the shadow of the comet. You will just see a combination of the light that is reflected, and diffracted. And then, in that situation, you will observe this extinction paradox. You will observe that twice the amount of light is changing direction. If you're in the near field, so to say, if you would put a plant in the vensterbank, that will not block that will just give a shadow, will not block. This is called the geometrical regime. So scattering cross section that is twice the geometrical cross section. So we now in this graph we have two asymptotic behaviors. Basically, we have the small particle limit where we have Rayleigh scattering, and we have the very large particle limit where we have this geometrical scattering. So what happens in between? So when the particle is scattering particle is about the size of the wavelength. That's not so easy. There are, of course, a couple of theories that try to tackle this. Because I want to show you only one, and that is mean theory. Mean theory is very rigorous. It is a solution to Maxwell's equations in spherical boundary conditions, which means that it exactly describes the scattering by spheres. So you can debate how useful that is for mathematics. And I'm always reminded of the worst joke in physics. Have you heard that? The first joke in physics? The punchline is, okay, let's assume the horse is a sphere to simplify the math. So basically what we're trying to do now is simplify the tissue into a particle and assume that the result is more or less valid. The worst joke in biomedical optics, by the way, is what do pirates and light have in common? They both travel at sea. Sorry about that. Okay, simplify the math. That is a cruel joke because this is the math. We're not going to go through that. Don't worry. Computers can do that. But so we started. Starts out with Maxwell's equations and then solves it for boundary conditions. You get these awful equations with series expansions and everything. But it does work. The computer can calculate this, so it's not that hard to do. You could go to the same website that I recommended to you before. You can find a calculator over there that does the work for you. So here you see the input screen. So what you need to put in is, of course, the size of the sphere, the diameter, the wavelength in which you're interested in of analyzing, the refractive index of the sphere, and the refractive index of the medium in which it is embedded. So that could be in air or in water. And then this basically is just for the calculation. So the number of angles that you have. So you don't actually need that much information to calculate the spectrum properties. You need the wavelength, the size, and the refractive index, and that's basically it. From that you can calculate, or me-theory then calculates for you the scattering efficiency, the scattering cross-section, the phase function, the anisotropy, everything. So this is just an example for red light, so 632 nanometers. Particle size of, doesn't say that, well, anyway, it doesn't really matter. It calculates all these efficiencies and cross sections for you. It calculates the phase function, so the angular redistribution of the light. It does that even for two polarization directions. It's even more fancy than what we did. So you can do that me calculation for different sizes for the wavelengths that we already had. And as you can see, for a spherical particle, these dots are then calculations. It nicely behaves as it should in the limit where the particle, the sphere, is really small compared to wavelength, and it just coincides with Rayleigh theory. It also behaves according to what we expected, according to geometrical theory, when the particle is really large, the geometrical limit, and in between gives you an in-between result.
Maybe it's that once again the extinction paradox.
Yeah, I was hoping you would ask that. What part do you want me to explain? Or try to explain?
Yeah, like I see the how is it in practice because I see the reflection and the refraction and I look at the equations, but I haven't didn't find the point on what this was solved.
The ultimate point is that scattering is the sum of all these contributions. So the scattering process is just redirection of light, and that can be a reflection from the surface. It can be refraction through the particle, but it can also be diffraction around the edge of the particle. And all these three components occur, and it depends on the exact size, the exact wavelength, the exact composition, which one will be dominant. So sometimes the reflection is dominant, sometimes the diffraction is dominant, and all that. For a very large particle compared to the wavelength, you can kind of split this intuitively into two components: light that hits the particle and light that passes the particle. Light that hits the particle is either reflected or refracted, just like in the water drop and the rainbow. And the light that basically does not hit the particle is diffracted around its edges. Now you can calculate the efficiency for the efficiency for light that hits the particle. Because it is so large, that should just be unity. And you can calculate the efficiency for diffraction of light that is diffracted around the edge of the particle. And by Babinet's principle, you can argue that that should also be the same as the geometrical cross-section. So the efficiency for that process should also be. And then then you have two efficiencies, both equal to 1, which both go into the scattering process. So adding them up gives 2. which means the efficiency of redirecting light by all these processes together is 2. So you remove light, there is a light redirected that is directly incident on the particle, but also some of the light that passes around the edges is redirected because of diffraction, and that also counts.
Okay. Yeah, but then it's still then some of these I don't know what these measurements are, this omega SC or sigma SC or QSC, that like somehow you have to take this into account to not like mix them up. Or
well, in the end, you make if you do a measurement, you can't distinguish them anymore. So then you just measure the net effect of what happens. The only thing is that what is a little bit paradoxical about it is that okay, I could take a very large particle. I could take a flower pot, and I could put it in the window, and then this is going to remove twice the amount of light that's incident on it. Yeah, but you will not observe that because what you will observe is just the shadow that has the same size as the pot itself. The light that whatever is diffracted around it, you will not observe the shadow. And if the situation is different, if you take a far away object like this comet, illuminated by an even farther away star, then you will not see a direct shadow, but you will see more the diffracted light. So you will not. It's difficult to observe. It's difficult to observe. If you would want to measure it, you would have to be able to measure all the scattered light in all directions around the particle. So just like with the flower pot, if you would put it in the window and you would look there, then you will not catch all the diffracted light.
Okay, but suppose you could catch all the diffracted light and everything.
If you had a detector that was only directional, only potent, and it's so good that it would make me very rich, if I would defend it.
Then what would you measure?
Then you would measure. Too, because then you would also measure the diffraction component. But yeah, and then you can even make it more complicated because what also happens, and that is also a little bit. So you have this light that. So let's say you have this big particle. You have the light that hits it. Okay, we understand that. That's easy. That gets redirected. But the light that passes it, so part of the light is diffracted around the edges. But if you look a little bit farther away, we have light that is propagating more or less undisturbed. If it's far away from the particle, it does not effectively see it. So then, if we start looking here in the far field, we get what we get as a contribution is the undisturbed light that passed the particle pretty far away. But we also get the field, the diffracted field from here. They will also interfere. So it will also depend then where you put your detector what you measure.
Yeah. I'll ask you afterwards.
It's complicated. Yeah. Yeah, no, so in the mean theory, so if you make the sacrifice that it's okay, I'll assume that particle is a sphere, then mean theory can calculate any size over wavelength range. Okay. This is, and maybe I went a little bit too fast on this thing. This is what I wanted to talk to you today. We've recorded this, but I also have two short videos that go a little bit slower on the same topic, so I'll link that as well. So it has the same information, but maybe at a slightly slower pace. So what we did this week basically is we discussed absorption and scattering by single isolated particles. So there's no way near tissue yet. We did need to do that because we had these efficiencies, cross sections, coefficients, phase functions, and isotropies, because now we have something to work with. These are the optical properties that we ultimately want to go. So then next week I want to start basically constructing tissue, or something that approaches tissue, by looking at collections of these particles. We did that already a little bit for the absorption, but we're also going to do that for scattering. So now we have light that will not be scattered only once by a single particle, but we can have multiple particles that scatter light once, or we can have light scattered by multiple particles. may seem after that absorption is going to be a little bit of an afterthought. It's not. We have Beer's law, and Beer's law holds along every path that the light takes. So even if we have light that is scattered multiple times, you can just apply, if you need to know something about the absorption, you can just apply Beer's law. Okay. I'll put the first assignment, the first graded assignment on Canvas this weekend. Part of it will be about the lecture of next Tuesday. But the first part are the questions that are on slide 52. So if you already want to, you can start with that. And the other part is about Monte Carlo. That is what we will cover next Tuesday. Then the due date of this first assignment is in 2 weeks. That's it. If you have questions, then shoot.
I have a question online.
Yes.
You said the first questions are on slide 52.
Yeah.
These questions you mean are the questions about Rayleigh scattering, right?
Yeah, I'll show them briefly.
Okay. Yeah. Perfect. Yeah. Thank you.
So in the room here, you seem a bit like a godlike presence because you come from all over the place.
All over the speakers.
I also have a question.
Go ahead.
You can make the assignment with a group of max 3,
Yeah.
right?
Yeah.
Okay, that was
Yeah.
my question, just to
Okay.
confirm.
Very
Thank
good.
you.
Yeah, so it's fine with me. You can do it alone or in a group of 3. Of course, the whole group will get the same grade. That's
Yes, of course. Thank you.
okay. All right, in that case, I wish you a very good weekend. And see you on Tuesday.
Thank you. See you on Tuesday.